Okay, in this video we're going to continue with constructing a very simple binary tree, class-based binary tree in Python 3. Again, there are lots and lots of different ways to make binary trees. This is just one way. The way you structure a binary tree can actually change how useful it is. Okay, so we are structuring this as a complete binary tree, which means when we add items, we're adding items one at a time, one layer at a time from left to right. So first item, and this layer is now complete. So we go to the next layer, left, we add B, to the right, we add C, this layer is complete, and then we start from left to right, adding items D, E, F, G, right? So that's the strategy we chose, but it is important to know there are many, many different types of ways to create these binary trees. All right, so last time we left off, we had a node, an init function that creates a node. The node just has a value, and typically this value would be more than just a letter, right? It's not particularly useful to just have some letter in here. What this would probably be is an object. It could be an object of a user in your system, and that object could have lots of different other information in it. Like it could be a dictionary of values. It could have first name, last name, telephone number, address, all the different things that you might have in any kind of database about a user, right? And then so value, we're just putting something in here just as a placeholder to explore the concept of a binary tree, but just know if you're actually using this in the real world, value would not just be a letter. That's mostly useless. Okay, it's very handy for us to use the letters when we construct the binary tree, because it shows us very easily what's happening within the tree. All right, but this value property on the node would usually be much more complex. Or you could even have multiple things on the node, right? I could have value and then another more complex value, self dot value, advanced something, and that could be the object or something like that. There's a lot of different ways you could do that, but just so you know, in the real world, we're not just making binary trees with letters on them usually. Okay, this is just to help us construct this concept of a binary tree. All right, so we left off, we have the node, right? And that's got a value, left and right property. And this is really all you need to make a binary tree. This class we called it tree, and it's just a wrapper around this functionality. So it connects all of these nodes together for you via an insert function down here. And it keeps track of the root node and the length. So it adds some functionality, but technically to have a tree, all you need is this node class, and you can connect things up manually. This just gives us extra functionality around this node class. All right, so we have the init function. The tree itself has a root, and that is the root node, and it starts out as none, and the length of the tree is just the number of nodes in it, and that starts out at 0. We set the length property so we can use the global length function. Get node, this allows us to get a node by index number. The concept of the index number we're using is abstract. We don't keep track of an index number anywhere, but in our understanding of how this works, we are mentally keeping track that the first node, the root node, is index 0, its left property is index 1, and then the right property is index 2, 3, 4, 5, 6. So we're not keeping track of this anywhere, but it is there in our abstract representation of a binary tree in our heads. So we can use the concept of an index without actually keeping track of it anywhere. All right, and so for get node, we do this in sort of a breadth first fashion. This is a common way to find something in a breadth first fashion. So later we're going to do a breadth first traversal and a breadth first search. Basically, you're just going to tweak this a little bit, right? And that's, I'm actually going to probably, since we already have this here, I'll probably leave that for you to do on your own, because it's just similar to this, but you'll add some additional features or tweak it just a little bit. All right, so that's get node. Once you have get node, get value is easy. Get value by index. We pass in an index. Well, just get the node and then call dot value on it. Right? So this is reuse. I could have all of this code again and then print out current node dot value, but that's a waste. I already did all this work with get node, so I just use that function that I already made, and then call dot value on the return value. Okay, so that's good. And then insert. Okay, so we use this one. This one too was much like our get node. It uses a breadth first sort of traversal to try to find a node that doesn't have a dot left or a dot right property. Okay, now this only works because of the types of binary trees we're building. This binary tree is a complete binary tree, and so that means we're adding items left to right on a particular level. So that means anytime we encounter a node that does not have a left property, that means that's where our new node is supposed to go. So imagine we had an H node, right? Where do we add the H node? Well, we go A. Does A have any children? Yes. B and C, this gets added to the queue. Does B have any children? Yes. D and E. C, yes, yes. So this is in our visit queue. And then we pop off D and we say, does it have any children on the left side? No. So that has to be where H goes, right? So we add H. What about I? So assume H is here. We do the same thing. D.left, does that have an item? Yes, it does. It's H. And D.right does not. So now we add I. And so we go through. The only reason that this works is because of the type of tree that we have. And that's important to know. There are different ways of adding things to a binary tree depending on the kind that you have. Okay. So this while loop, again, is sort of a breadth first traversal. So we have our visit queue. We add the root to the queue. And then in the loop, we continuously pop off that pop 0, and that's our current node. And we keep track of I. I starts at 0, and as soon as we find an item in here where we have current node dot left, as soon as that does equal none, then we're in this else block and we add our new node, right? Or if current node dot right does equal none, then we would be in this else block and add the new node. So this allowed us to do something like this with the binary tree, and we had this print tree function. Okay, this is the print tree function, and this is kind of calling a recursive method. We are not going to focus on this, so you can look into that if you want, but that's kind of outside the scope. But I wanted to add this in here because it prints out a nice binary tree structure for us to look at to make sure everything's wired up properly. So here we can specify how big we want our binary tree to be. We can make it 15 and then run binary tree, and now there are 15 items in here. Okay, so that's kind of where we left off. And what do we want to add next? Okay, so let's just paste in here all of the different methods that we might want to add. So after insert, we'll keep print tree kind of at the bottom. And there we go. Paste all these things in here. Okay. So what we're going to do is a traversal of our tree. And a traversal, there's different ways you can traverse the tree. A breadth first traversal would be to visit this node A, and then print it out, and then it's basically level by level, left to right on each level. So A, then B, then C, then D, then E, then F, then G. That's a breadth first traversal, and that's basically everything we've done so far. So you can mimic these patterns in insert or in get node, and both of these strategies are similar. They use a sort of breadth first strategy. Okay, so we'll leave this one alone. You should be able to get that one on your own based on the insert and get node implementations. The other ways you can traverse the binary tree, one other way is with a depth first traversal. Now there's actually 3 different ways that that traversal can occur. So with a depth first traversal, you have the concept of visiting a node. So when I visit a node, when do I print out the value? I can print out the value as soon as I visit the node and then visit the children. Or I can print out the node after I've visited the left child, and then I'll print the value and then visit the right child. Or I can wait and visit both children and then print out the value. Okay, so these are the 3 different ways that you can traverse a binary tree with a depth first traversal, right? So pre-order, depth first pre-order traversal is basically where you, before you visit both children, before you visit both children, you print out the value of the node. So this would be A, and then you visit B, and we print out B, and then we visit D, and we print out D, visit both children, there's none, we go back up to B, and go to E, we print out E, visit both children, right? So we have A, B, D, E, and then go over here to C, print out C, visit F, print out F, visit, nothing, go to G, print out G, visit. That's pre-order. You always print out the node before you visit either node. In order is you print out the value only after you visited the left node. And then, so you visit the left node, so this would be, we visit A, we visit B, we visit D, D visits its left node, which is none. Now we print out D, visit the right node, which is none. We go back up here, now we visited the left node, so it's B is printed out, so now we have D, B, and then we visit the right node, we visit left, nothing there, we can print out E, visit right, go back up to B, now we're back up to A, and now we can print out A because we visited that whole left tree. Okay, so that's kind of the idea between of an in-order traversal. And then there's post-order. Post-order is you have to visit both of the children before you can print out the value. Okay, so again, this makes use of what we call a visit function. Okay, and it's a recursive kind of style function. So visit, I have the kind of the method signatures outlined for you. Breadth first traversal, you can do on your own based on the other items. But DFT visit, this is a depth first traversal, and this is our visit. This is our recursive function. And it's going to take these items. These are the parameters. It's going to take a node, and then traversal is just going to be a list. So the way we're going to do this is the breadth first traversal is going to start out as an empty list. And then you're going to add items to it as you traverse the list. And when you get finished, you should be returning the traversal list. Okay, so same thing here. Traversal, when we talk about traversal, that's going to be a list. So basically what happens in all of these, order type, what type of order? Is it pre-order, in order, or post-order? So each one of these three traversals is going to call this function. Right, so we'll have something like this, traversal equals an empty list, and then we're going to say self dot underscore DFT visit, and we want to pass in our starting point, which is self dot root. We're going to pass in the traversal list, and this function, DFT visit, is going to decide when to add a node's value to that traversal list. And then the last item is which order type, right? So this is pre-order, right? So we're just going to pass in pre-order here. And when we get done, we're passing in this list. This list is going to get modified as we pass it in. So each time DFT visit is called, DFT visit is going to call itself as well. But this traversal list is going to be modified. We're going to add items to it repeatedly. When this call is all finished, this list will have been modified, and we can just return it. Return traversal. Right? Okay, and also this isn't self. Okay, that's one other thing I need to explain. There are, in classes in Python 3, there are class methods and static methods and function decorators that you need to use for those. I'm trying to avoid all the complexity around that. So if you notice, this method here does not start with the self parameter. Okay, so this is not an instance method. Okay, now it's not technically a static method or a class method either. It's just a function that happens to be attached to this class tree. Okay, so it's just a plain function that happens to be packaged with this class. All right, so I can't use self and access underscore DFT visit. This won't work. What I had before here, this will not work because we don't have that self parameter up here. Okay, so the way I access this function is by way of the class itself, TREE. So that is my class name, and this function is just another parameter or another attribute on this class object. Okay, but this is not accessible from an instance. So I cannot say self._DFT visit. Okay, now this probably wouldn't be the ideal way to do this in a professional environment, but again, I'm trying to avoid all the complexities of static methods and class methods and function decorators and that sort of thing. Okay, so we're going to try to keep this simple, relatively simple. All right, so we see here the important bit here. When do I do it this way? When do I say class name dot, right? That's when my function does not have a self property as the first parameter. Okay, when it doesn't have the self parameter, then that's just a plain function. All right, which means you have to use tree dot to access that function. And you only want to do that, of course, when this function doesn't need any of the properties of the particular tree. That means we don't need self.root, we don't need self.length, we don't need any of these other methods, right? So you only want to do this style when this function does not require anything about the instance, right? So we're actually just making a function and we're providing the function with everything it needs. It doesn't need to know anything about the instance, so we don't need to provide it the instance. All right, so we have our traversal list. We have tree dot underscore DFT visit. So this part is important, right? The way you call that is with the class name dot visit. And again, that's because we don't have the self parameter there. All right, what are we passing in? Self.root, the traversal, and then what type of order. So all three of these are going to be, we have the depth first pre-order traversal, in-order traversal, and post-order traversal. All three of these are going to be set up this way. The only difference really is going to be this last item. So I'm in the pre-order traversal, so I say pre-order. So you can do these yourself. It's only a couple lines of code, a few lines. And what we have to do here is in the depth first visit, we're going to have to use recursion. Okay, so and again, it is important that this is just a plain ordinary function that's attached, that happens to be attached to the tree class. Okay, it's not a static method, it's not a class method, it's just a method that is attached to the class, not the instance. Okay, so whenever you use recursion, you need some sort of base case, right? So when I'm recursing and I call this function over and over and over, at some point I have to stop calling this function, otherwise I'm going to be in an infinite loop, or the call stack is going to be exceeded. So when you use recursion and you go more than, in Python 3 it's set at about 1,000, if you recurse to a depth more than 1,000, that's called blowing up the stack, or Stack Overflow. You might have heard of that website. It's a really good website. But that's the idea. The stack, the call stack, it only can hold 1,000 items in Python. You can expand it, but by default it's just 1,000. Okay, so that means I can't, every time I call this function, that means I can't keep recursing. At some point I have to stop recursing and just return, right? So the base case, this is what that's called, base case. We can say if my current node is none, then I don't want to do anything. I'm just going to return. So first of all, what is this depth first that we're talking about, right? We kind of went through the pre-order and post-order, but the idea here is I'm visiting a node and then I have to visit the children. Now at some point I'm going to print out the value of this node, either beforehand then visit a child and visit all the children, right? Or I can visit this node and visit that node and then print after I visited the left child, and print the alternative. The third one is post order, where I can print after I visited both children. Okay, so this DFT visit is meant to represent the act of visiting one of these nodes, right? So when current node equals none, that's like over here in our tree, we're going to go to D and we say visit D.left. Okay, well there's nothing here, so we pass in none. D.left is none, right? On that node, we start out self.left, it starts out as none. So unless we explicitly change that, it's going to be none. So down here, D, its left value is none and its right value is none. So back down here, when we are visiting a node, if that node is none, then we don't do anything because there's nothing to print out. There is no node there. So there's no children to visit and there's no value to print out. So this is our base case. This is our recursion base case. Okay, so that gives us a base case where we will eventually break out of the recursion. Okay, so all recursive functions need some sort of base case like that. Now what we have to do is, we know at some point we're going to be visiting the children. We have to visit the child nodes, right? So we're going to be using this function again. Now again, this is just a plain method that happens to be attached to the class tree, right? Because there's no self parameter. So this is tree.dft visit. Alright, and we need to pass in a node. Well, the node we're passing in is current node.left, because we're going to visit the left node, and we want to pass in our traversal list. And then what order type? Well, whatever the order type we got here is going to be the same order type, so we can just pass that in. Okay, so, and then eventually we're going to have to visit the right child. Right, so the same function call and node.right instead. Now this isn't going to do anything yet, right? Because at some point we need to add to our traversal list. We need to add the current node's value property. So if it does have a value, if current node is an actual node, then we'll get to this code here. If not, we'll return before we ever get here. So at this point we know current node is an actual node. So current node, that actually is something, and then dot value is an attribute, not a method. It's an attribute. So the node's dot value. Okay, so the root node, for example, would be A, and then the next item would be B. So current node, at some point we need to add this value to our traversal list. Okay, so in a pre-order, we would add it here. Traversals.append, and we want to append this current node.value. Right? And then we'd visit the left node and the right node. But then as soon as we visited the left node, we'd start this function call again. If left was none, we'd return. Otherwise, we'd append the traversal there. Okay, so this is in the case of a pre-order traversal. Right? If we wanted to do an in-order traversal, we would have to move this down here in between the two visits. This is the visit of the left child, and in order, then we print out the value or add it to our traversal list, and then visit the right child. Now if we wanted a post order, then that means this code would have to go down here. Okay, so we could make three separate functions. We could have a pre-order visit, and we could have a post-order visit, an in-order visit, all three of them. Or we could just pass in this order type. This order type tells us when we should be adding to our traversals list. This order type is going to be for pre-order traversal is pre-order. So here, all we have to do is we say if order type is equal to pre-order, that's when we add or append to our list. But either way, we're always going to be visiting the left and the right children. It doesn't matter what order type, we're always doing this. So here we're just checking to see if the order type is pre-order, and if it's pre-order, then this is where we're supposed to add to our traversal lists, right? Now, if it's an in-order traversal, then we have to check to see if this is in order instead of pre-order. And if it's in order, this is where we add to our traversals list, right? And then the last one is post order. So if order type is post order, this is where we add. Okay, so what's nice here is since we were doing the same things for all three of these functions, we're visiting the left and the right child. The only difference is based on the order. So if we pass in what order type we're using, then we can use this same function for all three of these traversals. Okay, for the pre-order traversal, in-order traversal, and post-order traversal. All right, and so we can see what this looks like. We can scroll down and see what the post-order traversal looks like. So we do tree.print, and then we want to add some functionality here. We want to print. This is going to be a depth first pre-order traversal colon, and then all we want to do is print, and this should return a list, right? Because if we go up here, we want depth first pre-order traversal. This returns that traversal list. So every time we call this visit function, this list gets modified. So every time this is called, and it's called repeatedly, recursively, until we get to this recursion base case, the traversal list is modified. But that's what gets returned. So the value we get back from this function is this list, traversal. All right. So oops, need to copy that. Make sure I don't misspell it. All right. So I'm going to call this method tree. Our tree is T, right? We created a tree here that's T dot, and then depth first pre-order traversal, and we'll call that, and that should return a list. So let's see how this looks. Traversals is not defined. That is at line 88. Oh, it's traversal. There we go. Okay, I think that's right. Let's see if there's any other errors. 2 positional arguments but given 3. That is at line 90. Dot left. And let me check through this. DFT visit. Should take 3. Oh. Maybe I do need the class method here. Let's try that and see if that fixes it. This was what I was trying to avoid. I'm not sure why it's not working on this one, and it worked on the other one. Takes 3 positional arguments. forward given, line 105. Oh, I'm using the wrong, this is DFT visit because, there we go. Alright, I don't need the decorator. This is DFT visit. I have DFS visit. That's for something else. This is for the traversals, depth first traversals. That's the T. Okay. Later we're going to do a binary search, and that's depth first search. Alright, so that's an oversight on my part. DFT. So this is recursive. We have to use the exact same name there. So that's my fault for using autocomplete and not paying attention. Okay, so this is calling DFT visit, so that's correct. All right, so some of these errors can be tricky to find. So always just look at the line number and kind of see if you can tell what's going on. Look at the error, 3 positional arguments with forward given. That tells me that there's something squirrely going on with whether or not this is an instance method or not. All right. And so then I can call binary tree. And here we go. We've got our depth first pre-order traversal. Now again, remember, pre-order means that the node is printed out first, and then the children are visited. So in this case, this should be A. We print that out immediately, then we visit the left node. So then it'll be a B, which we have A, B, right? And then we visit the left node. So then that should be D, so A, B, D. And we visit the left node H. It should be H, right? And it is. And then we visit the left node, nothing there. And then we visit the right node, nothing there. And we go back up to D. We've already printed out D, we just need to visit the right node now. And now that's I. We visit left, then right. Nothing, go back up, go back up. We've already printed out B, so we go to the right, and that's E. We visit left is J, no children, go back up. Visit right is K, no children, go back up, go back up, go back up. And now we're at C. Okay, so you see that this is working properly, but you need to verify that with each one of these that you make. You need to go through this whole list and make sure it is actually printing out the depth first pre-order traversal properly. Okay, so there's 3 of those. You should be able to do the other 2 quite easily. So because we've made the recursive function, and these 2 are basically just mimicking what's in here, except you change what order type it is. Right? And then the last items we do is a breadth first search. Okay, so I'm going to leave these to you. The concept here is you go in a breadth first fashion searching for items. So this breadth first search is very similar to get node by index. So get node, right? You have a queue. You start with the root and you pop off an item. But instead of while I is less than index, it's basically while I is less than the length of the tree. And you go through and visit each of the items in a breadth first fashion. And it'll be A, then B, then C, then D. And what you want to do is actually you want to find out when the value of the current node is equal to the value you're searching for. So if we could look down here, breadth first search, and it's going to return the node. That's why it says node at the end. We're looking for some search value. So for example, I might be searching for the letter F, right? And this is more something you would do if you don't know what's in your binary tree. The way we're constructing this tree, we know if F is going to be there, and because we're just doing A, B, C, D, E, F, G, we actually know where it is. We can do some math and figure out what index it's at, and we could know that without actually searching. The search method is more for a tree where you don't know what kind of data you have in here, right? The depth first search is more for a particularly structured binary tree where the items to the left are always lower than the items to the right. And that gives us a really nice strategy where we can search for something, and at most it will just take one traversal of one leg of the tree, right? But we don't have a tree like that, so we're still going to have to search several times. So when we do a depth first search for this tree, we're going to have to just go through, and we might take many different legs of the tree to find our node, right? But the breadth first search is the same. You just go one node at a time and search for your value. When you find your value, then you return that. Okay, so here's where we had that additional recursive function. This got us confused a little bit last time. The DFS visit, right? So this is the depth first search visit. So the idea is exactly the same, but instead of traversals, we're not keeping track of our traversal. We're looking for a particular node with this value, search value. When we find a node with that value, we return the entire node. Okay, so that's what you should be returning here, the entire node. All right, so that should give you more than enough to get started and continue working on these on your own. You should have enough information to be able to complete these pretty easily. All right, so that should do it for simple binary tree. I'll go through and scan the code one more time so you can pause and take a look. We got our node. Math is for the print tree. And then here's the tree class, the init function, length, get node, and get value. And then insert. And then the breadth first traversal we did not do. You need to finish this, but keep in mind the traversals always return a list of values. Alright, and then we did the depth first visit. So these two go together, and all the other depth first traversals are real similar to this one. And then you have breadth first search and depth first search. And remember, those return nodes. Both of these return the node, not just the value. You already have the value, right? You're passing in the value, so you don't. It's not useful to get the value. You want to get the node back. Okay, and then here's the tree print. This voodoo is outside the scope of this, but it does print out these nice little binary trees here. And then down here, this is testing our binary tree. All right, that should do it.